Hello and welcome to CPSC 5011, Object-Oriented Concepts. My name is Sheila O. I'll be the professor for this course. So in Lecture 1, we're going to be talking about quite a few topics, including type abstraction, information hiding, coupling, cohesion, and class design. So we'll start the lecture with a few definitions, the first of which is data type, or simply type, which is a classification of data which tells a compiler or interpreter how the programmer intends to use the data. Abstraction is the purposeful suppression or hiding of some details of a process or artifact in order to bring out more clearly other aspects, details, or structure. Information hiding is the purposeful omission of details in the development of an abstract representation. Information hiding is what allows abstraction to control complexity. Coupling refers to the extent to which one component uses another to perform actions. Generally, a goal is to reduce coupling between software components. And cohesion refers to the extent to which the actions of a component seems to be tied together in purpose. Generally, a goal is to increase cohesion within a software component. Now, there are multiple classes of data types, some of which we've actually already worked with in previous courses. The first is the primitive data type, which is built into language implementation. We've worked with numeric types such as integers and doubles and booleans, for example. The composite type is derived from more than one primitive and is combined as data structures. So we have also worked with arrays. We will introduce a record, which is also known as a tuple or struct. The struct is something that is used in C++ and C#, a union, a set, and an object. Other data types are enumerations, string and text types, pointers and references, and function types. And finally, we have abstract data types, which is any type that does not specify an implementation, for example, a queue, a set, stack, tree, graph, list, hash, or map, etc. Some considerations in terms of type include type checking, which verifies that operations are performed on a type are meaningful and legal. We have statically typed languages. For example, Java is a statically typed language. Later on, we'll be talking about C++. Here, the type is associated with an identifier. In this case, we have a data type that precedes the variable, and that data type will determine by the compiler how much memory is to be stored, what type of data should be stored, etc. So the compiler verifies, and there is no runtime overhead. Dynamically typed languages, in contrast, have a type that's associated with a value. This type is actually then checked at runtime. And in the case of dynamically typed languages, a value that is assigned an integer can actually then be at a later point assigned a string. Typecasting, there are two types. The first is implicit, also called coercion, and there's also explicit typecasting. We'll now talk about types in software design, the first of which is procedural or structured programming. So procedural structured programming actually came about due to concerns about the cost of code. As development of software became more costly because the solutions were becoming more and more complex, there was a proliferation of what we call spaghetti code, which is code that had little inherent structure and no discernible control flow. This software was very difficult to understand, test, and modify when its control flow cannot be easily traced or predicted. So we came upon what we call the idea of functional decomposition, and this allowed us a support of a clear control flow and the ability to clearly define composite types. However, one limitation is that structured programming has little persistent connection between the functions and data, because global data, or the passing of parameters, is the primary means to share data. We also will look at modular programming, where a module is defined as a set of procedures with its related data. This type of software design promotes low coupling and high cohesion, which is the ideal in software design. The lowering of the interdependency of two different software elements or components makes it more likely that a change in one element does not force a change in the second, and this results in better software maintainability. And since change for a feature is restricted to a single module or element, cascading changes are then avoided. For defined types, a separation of concern, defining a separation of interface and implementation, also reduces the maintenance costs if the modules are highly cohesive. There are many layers of abstraction that are covered in BUD Chapter 2. I'm not going to go into these in much detail, but the slides are linked at the bottom of this page, and so you can take and review those. The slides are just going to be an overview of what is actually in the book. There are additional forms of abstraction, which includes the division into parts, also known as HAS-A. Division of parts takes a complex system and divides it into its components, which then can be considered in isolation. What this really allows us to do is, because these components are actually isolated, one component can be actually worked on in conjunction or in parallel with other components. This is a promotion then of low coupling, and some examples of this are, for example, a car has an engine and that engine has a transmission. A bicycle also has a wheel. Specialization is designated with is-a statements, and it takes a complex system and views it as an instance of a more general abstraction. The example in the book has a hierarchy that defines this specialization model. At the very top, we have a means of transportation, which can be specialized to a wheeled vehicle, which can further be specialized to a bicycle or an automobile. The means of transportation, again at the top, can also be specialized as a pack horse or other means of transportation which are not defined within the hierarchy in the book. So, in summary, or examples of these are: a car is a wheeled vehicle, which is a means of transportation; a bicycle is a wheeled vehicle; and a pack horse is a means of transportation. It looks like a couple words are missing from this slide, so I will update those slides on Canvas after this lecture. Composition is a form of HAS-A and is characterized by having primitive forms, rules for combined old values to create new values, and the idea that new values can also be subject to further combination. An example of this is regular expressions. Regular expressions are simply a technique for describing sets of values, and what you have in terms of a regular expression is a combination of multiple regular expression in combination, or a rule to then apply to a finite string of letters or characters. Patterns are also another form of abstraction. This is another attempt to document and reuse abstractions and descriptions of proven and useful relationships between objects are defined within patterns, which can help guide the solutions of new problems. So all of these additional forms of abstraction, whether it be has a, is a, composition, or patterns, will actually be described in more detail in later chapters of the book, as well as subsequent lectures in this course. As mentioned in the book, procedures and functions represent the next improvement in abstraction in programming languages. Procedures allowed tasks that were executed repeatedly or executed with only slight variations to be collected in one place and reused, rather than being duplicated several times. In addition, the procedure gave the first possibility for information hiding. Now, one thing that was mentioned in previous programming courses is that if you have code that is repeated, we generally try to modularize or functionally decompose that so that we have one point or one place that we're actually making changes, and the process then can help promote maintainability and readability, and will make the code more concise. So we've already mentioned that these structures or procedures, or structural programming, will allow us to support clear control flow, functional decomposition, and the ability to clearly define composite types. The book defines an example of a stack, and in this stack there is globally defined a data stack variable that is implemented using an array, and a data top variable which is initialized to 0. There are also functions init, push, top, and pop, which are implemented much in the same way as they would be as member functions in a stack class. Now, one of the issues here is that we have two global variables, and there's no way to actually limit the accessibility or visibility of these two variables. And so this is one violation or failure of information hiding. In order to achieve abstraction, we would want to have a publicly interfacing component as well as private implementations. Now, David Parmes, who popularized the notion of modules, had two principles, one of which was that one must provide the intended user with all the information needed to use the module correctly and nothing more. And in this intended user, they're talking about the client. And one must provide the implementer or the designer with all the information needed to complete the module and nothing more. So it's this need to know basis is violated within the implementation of a module, where we're not actually concealing any of the information that is dealing with the implementation of the stack. So this is again another violation or failure of information hiding. We move on to the definition of an abstract data type. A reminder that an abstract data type is any type that does not specify an implementation. What this means, for example, in the stack class, is the internal implementation can actually be defined in multiple ways, or multiple different ways. One way would be to use an array. One way would be to use some type of linked list structure. So there's a separation of the internal implementation with the external interface. So the external use by the client is actually really important, because the client is not concerned with the implementation details. The client is then dependent on and codes only to the interface, not to the implementation. For the stack, for example, all the client knows is the functionality, the public functionality of the abstract data type. For example, the constructor is publicly defined and is accessible for the client, and so therefore the client can create a new stack instance. Once that instance is created, the client can call different functionality to push different elements onto the stack, pop elements from the stack, peek to see what is at the top of the stack. And this internal definition by the class designer will not impact this client, will only impact the class designer. What this does is results in reusable and testable code, and the idea of an abstract data type is that we are increasing cohesion because what is defined in this abstract data type is information and data that should be cohesive and grouped together. Now, object-oriented programming is the combination of an abstract data type with encapsulation, type extension, as well as substitutability. Again, we'll introduce the idea of encapsulation in this lecture, but the two others we'll be talking about in subsequent lectures. Next, we'll talk about a class construct, and when we're talking about it as a type definition, we have this encapsulated abstract data type where we have information that is information or data that is privately encapsulated within the definition of this abstract data type, and public ways to interface with that data. External dependencies are minimized, and this is supported in modern object-oriented programming languages such as C++ and Java. For example, let's take a look at a queue, which, similar to a stack, has a way of interfacing with this abstract data type, including functions like enqueue, dequeue, empty, the constructor. The implementation, again, as similar to the stack, can be either a static or dynamic implementation using a circular array or a linked list. And the client's use of the queue is not affected by the internal implementation. Moving on to class terminology, a class method or member function is a function declared in class scope. An instance of a class is an allocation or declaration of that class definition, and member functions must distinguish between multiple instances of the class. This pointer holds the address of the active object, and an implicit parameter is an implicit parameter passed within each member function invocation. And one thing that we will talk about in detail is this idea of internal state, which is the value of internal data members at a given point. Now, take a look at the stack or the queue. It doesn't really matter. Now, in terms of a stack, there are conditions in terms of the state that allow us to call different functionality, which will allow us to keep the object in what we call a valid state. For example, in terms of a stack, once we initialize a stack and create an instance of a stack, the constructor is called, and in the initial state, the stack is empty. Once we push elements onto the stack is no longer empty. If we pop a stack, we must pop if the stack is not empty. So what is common between all of these functions are this idea of emptiness. So the internal or the initial state of the stack class or stack ADT is that it is going to be empty. Later on, we're going to be talking about this idea of the conditions, or what we call a contract, for use of different functions. So for example, a push function can only be called, and again, depending on the implementation, can only be called if there is a stack that is not full. If a stack is full, then we cannot push unless there is some type of resize capability, but again, that is an implementation detail that is hidden from the client. Now, in terms of POP, a precondition or some rules of use for the POP is that it cannot be empty. Generally, in terms of the Java util definition of stack, there is going to be an exception that's called if we try to pop from from an empty stack. But again, that is an implementation detail that can be modified depending on a different implementation of that particular class. So in terms of an object definition, an object is a self-contained entity that has data and operations encapsulated, an instance of an ADT or class that has internal state, so the value of all the fields or properties, and the class should control that state by minimizing sets and gets. One thing that you'll see a lot of programmers do is automatically generate all the setters and getters for all the private fields that are defined within a class. There is a downfall to this because what we're trying to do here is that if we're actually wanting to control the internal state, that we should really have control over what and how these fields are going to be manipulated. Gets, by definition, really shouldn't be manipulating or are restricted from manipulating the fields, but the setters or mutators are capable of changing the value and therefore changing the state of a class. So again, we'll talk about that more later, especially next week when we talk about contracts. Behavior is something else that we need to consider. So in terms of behavior, we also think about the operations or the functionality that is defined. And within this public functionality, state changes can also be triggered, and those should remain consistent. And finally, the identity can be defined by the name, which is relevant to the static type checking, or as well as the value, which is related to dynamic type checking. Moving on, we talk about object-oriented tenets or principles, and if you've looked at any book or website, these three things are generally mentioned, which is abstraction, encapsulation, and information hiding. Again, we've talked about a few of these things already, but we'll formalize this in the coming slides. And just to reiterate again, central class design principle is this control of state. In object-oriented programming, the implementation details are abstracted away. What that means is that the application programmer or the client does not need to know or care about how type is stored or manipulated. This is just as is the case with built-in types, as well as, for example, any of the Java util scanner, random, stack, anything that you've used previously, where you're really interfacing with the public functionality that is defined instead of the implementation details. The application programmer or the client, again, is not responsible for initializing the object, maintaining the consistent state of the object, proper manipulation of that, and bounds checking. All of those are implementation details that the class designer is responsible for. And an incompetent or malicious programmer cannot then subvert the type. So again, we'll talk a little bit about this idea of responsibility, of what is whose responsibility. And one thing to understand here is that the client or the application programmer is really just responsible for utilizing the public functionality in the proper way. And those rules are generally going to be defined, as we mentioned, by this idea of a contract. For example, this idea of a precondition for popping a stack would be that that stack is not empty. So as long as the conditions and rules of using that particular publicly defined function are maintained, then that client should be able to rely upon the class or the instance of that class or the object to remain in a consistent state. All of these other things that were mentioned below are really, again, the responsibility of the class designer and are not in the domain of the client or the application programmer. One thing I didn't mention in the previous slide was that a lot of times a class will provide the ability for the client to be able to check the internal state. So for example, in terms of a stack, there is an empty function that allows the user to check whether a stack is empty, and that check can happen prior to calling the pop function. So the next tenant is encapsulation, where we're wrapping up a type definition in one class. This allows us to have low coupling, so no extraneous functionality or data is defined within the class, and no external manipulation of the data is also happening. So one thing that we really want to try to avoid when we're defining a class is to have too much happening within that class. There's this tenet or principle of what we call a single responsibility. A class really should be doing one thing. That goes at a lower level in terms of methods or functions, where the function should again also be doing one thing. So if we have, for example, one type of class and another type of class, and both of them have the ability to access or manipulate a common field, then this idea of an external manipulation will not hold, and we would not have low coupling. So just be careful in terms of how you define your classes to ensure that we have low coupling, and later on in terms of high cohesion. This idea of having multiple sources being able to manipulate the data would actually again violate encapsulation, because again the idea of encapsulation is that you're hiding and wrapping up that data in one place, and so that data is protected. High cohesion is also promoted, and all the needed data and functionality are contained within that type definition. So again, it's not spread across multiple sources or classes. And this allows for and promotes maintainability. The creation of abstract data types allows us to separate the implementation from the interface. The implementation is hidden, where we can only interface, or the client can only interface with what is publicly available, and the client has no knowledge of the implementation details, and those implementation details can vary. So the client code is only dependent on the interface. This is robust in the way that external forces, as mentioned before, cannot put that object into an invalid state, and it's extensible. This idea of implementation and interface separated is clearly defined in C++ by actually having two separated files, which we call a header file, which contains the interface, and an implementation file, which contains the implementation details. Within Java, generally we combine the private and the public within the same, and so because of this combination, the information hiding is not fully realized. This separation of implementation and interface is what we call a separation of concerns. So we'll transition now in terms of class design. And again, a lot of this stuff will be covered in more detail in subsequent classes, but just to overview, we have what we call a type definition, where no memory allocated until you're instantiating a new instance of that class, which is called an object. Accessibility can be defined as public, protected, and private. We've covered private and public, but we have not covered protected, which will be defined later on when we talk about inheritance and this idea of specialization. Data, we have instance data, which exists for every object instantiated. Instance data can also be defined as the fields that are defined in a class. And then you have what we call class-wide globals, which are static members. There's one copy for the entire class and are independent of the objects instantiated. class design functionality includes a constructor which sets the object in a valid initial state. This is explicitly defined with the new operator and implicitly defined in C++, for example, by allocating memory on the stack. Later on, we'll talk more about memory and the implication of defining things on stack and heap. Everything in Java, for example, is defined on the heap. In C++, there's a combination of the two. The constructor is also responsible for initializing data and allocating any resources necessary. Accessors provide a controlled way of accessing the privately defined fields within a class. Accessors or getters should be const, meaning that accessors should not change or update any portion of privately defined fields, and the state of the class should not be updated. Mutators, on the other hand, are generally going to be altering the state, but it's a controlled alteration of that state. There is going to be a check of values, and we're going to discard, for example, any out-of-bounds values, and you'll be providing default values for these as well. An example to consider is a class that actually defines a fraction. And in terms of this fraction, there may be setters for the numerator and the denominator. Now, in terms of the denominator, one thing that we need to consider is that we cannot have a denominator that is equal to 0. This would be considered something that is out of bounds. Now, we have a couple ways of actually handling this, but again, this is an implementation detail where we can defensively decide to make a check to decide whether the incoming parameter is going to be in the bounds. So it's a validation of the parameter. Otherwise, later on, we'll talk about this idea again about a contract, which will be the rules for actually using this particular mutator and having the desired results, where the state is still going to remain in a valid state after the call to this particular mutator. We also have, in terms of class-assigned functionality, private utility functions, which will support reuse within the class, protected interfaces, which is a utility to be inherited by child classes. Again, we'll talk about protected interfaces and public protected functionality at a later point. Public interfaces, which support type definition, and minimum functionality is it's the minimum functionality needed by the client, and any cleanup, which is bookkeeping, for example, static data members. C++ also has this idea of a destructor, which will deallocate resources and memory. And Java has a finalized function, which is called when the garbage collector collects dead objects. In terms of standard class design will encapsulate data and the associated functionality, and it should also control internal state and access to the data and state transitions. So this will be the responsibility, again, of the class designer and should not be the responsibility or the concern of the client or the application programmer. The class methods include, in summary, constructors, accessors, mutators, private utility functions, and for C++ may also include destructors, copy constructors, and overloaded assignment operators. These will all again be discussed later on after the midterm when we introduce C++. And type is driven by public functionality, that which is essential to external manipulation of that type. So why do we have constructors? Constructors remove object initialization responsibility from the client. Again, what we mentioned in terms of the separation of concerns is that the client really should not be concerned with the implementation details, and the initialization of the object is part of the implementation details and should then be moved to the responsibility of the class designer. Objects will be automatically placed in a valid initial state upon an instantiation. So again, this is the responsibility of the class designer to make sure that the constructor puts an object through the initialization of the different fields that are defined within that class, and making sure that everything is within a valid initial state. So upon creation of that object, if it's in a valid initial state, then there are going to be certain public functionality that is available and accessible to be called on that particular object. Failure to initialize does not mean that the data has no value, but it does mean that there are limitations in terms of what you can actually do with that particular object because it hasn't been initialized. And a class without constructor yields an object in an indeterminate or valueless initial state. Private utility functions, also called private member functions, will provide functional decomposition, improve readability and maintainability, encourage consistent behavior, and encapsulation controls the accessibility so that application programmers do not have access to private utility functions or private member functions. Now, one thing to understand is that private member functions also promote this idea of single responsibility. In terms of a function, again, a function really should be doing one thing and only one thing. And so these member functions, whether they are created for organization, for maintainability, or for reuse, there's many reasons for creating them, but again, these are not accessible by anyone outside the class because they're going to be privately defined. Setters and getters provide a controlled access to an object's internal data. What this means is that privately defined fields can only be accessed through a public interface. Now, a client programs then to an interface and not the implementation, and this promotes software maintainability because there's a separation of concerns. The client responsibility is only to abiding by the contract and the rules of using a public function, and the class designer is then responsible for the implementation of that class. Accessors expose part or all of an object state. This can be explicitly defined, for example, in a stack with the empty function, where the client can then check the state of the object, whether it is empty or not, before it calls, for example, the pop function. Mutators can change the object state, but does not necessarily change the object state. For example, if we have, again, a stack, and we push an element onto the stack, and the stack happens to initially be empty, then the state of the object changes from empty to not empty. But if you push another element onto the stack, the state doesn't change. It still remains not empty. Later on, you may pop, and say you have 5 elements on the stack. If you pop, then it still is not empty, and you can pop again, and you would have to pop another 3 times until the object state changes to empty. Mutators should be conditional, and a class designer should determine when it is appropriate to reject a change made through a call to a mutator. We mentioned a few ways when we were talking about the fraction class, one of which is a defensive validation, and the other is to define a contract or rules of use of that mutator. Now, the idea of a destructor is really only relevant when we're talking about C++, where destructors are what we call resource managers that release internally allocated heap memory. As mentioned in a previous slide, C++ has a way of allocating both stack and heap memory. Again, more on this later. And destructors may also track the number of active objects, decrement reference counts, close files, etc. Note that this idea of a destructor is not available in Java. Java has a garbage collector that is responsible for reallocating memory or deallocating memory, though you can use the finalize method to aid in garbage collection, and it's not effectively used in C#, and C# also uses a garbage collector.